Main body of the scheme to JavaScript Transpiler. This is a deeper dive into source code rewriting technology. It's a follow-up to a previous video about transpiling scheme code to JavaScript. The grammar is less than 2 screens long. For certain edge cases, we want to explicitly match for special cases in the scheme code and to convert them in particular ways in JavaScript. The rewrite specification corresponds closely with the grammar. The rewrite specification is only a couple of screens long. There are less than 100 lines of code in the grammar and less than 100 lines of code in the rewrite specification. This would take many more lines of code to write in some general-purpose programming language like Python or Rust. It's not as small as a regular expression, but it does a lot more. Let's look only at the grammar and rewrite for the if-then case. The grammar specifies 5 submatches. Open parenthesis, the keyword if, something matched by the guard rule, something matched by the then-expr rule, and a closing parenthesis. The match branch is tagged with the name if-then. The matching rewrite rule inhales the 5 submatches, shown inside the square brackets, and composes a result string, shown on the right-hand side of the equals sign. Here, I show the correspondence between the subpatterns and the parameters to the rewrite rule. The parameters are little parse trees. The RWR DSL walks the trees and pulls out their final string values. Here, I show how the rewrite string is constructed. I use a pair of Unicode quotes to enclose the string. The composed string consists of raw characters, marked by purple dots, and string interpolations of the tree-walked submatches, circled in brown. To cross the chasm between scheme expression semantics and JavaScript statement semantics, I invented 4 small functions that operate on a stack of expressions: push, set, merge, pop. The generated code relies on these functions. I've contrived a simple example to show how code is generated for an if-then-else expression. We pattern match the incoming text, and if we see a particular pattern, we send it to the rewriter to create a different string for it. In this case, the if-then-else is exhaled as a template enclosed in push and merge function calls. Most of the template consists of boilerplate raw characters. The template uses interpolations for the guard, the then part, and the else part of the if statement. I will drill down and show how the then part is generated. The rest is similar. To map scheme expression semantics onto JavaScript statement semantics, we use the helper functions and guarantee that the then part and the else part set the topmost expression to a correct value. The whole JavaScript if statement is bracketed by a push and merge set of operations. Push creates a slot where the then part and else part can leave results. Merge is used to promote the final value to the next outer bracketing expression value. The code might contain nested ifs, so we need to deal with this stuff in a recursive manner. These helper functions are used in many other places in the rewrite to handle things like function definitions, conned expressions, and so on. Here, I only show what happens with the if-then-else code. After a bunch of pattern matching and rewriting, we generate the first cut JavaScript code for the then part. The generated code is legal but clunky. The code generator relies on rules in the rewrite spec to generate snippets of code for S expressions all the way down to numbers and variables, then glues all the snippets together to form a final result, which gets passed back up to the very top. We can easily remove some of the clunky code by using yet another stage of text rewriting. This is called peepholing. We write a pattern to find all calls to the set function, then weed out all of them except the last one in each control flow branch. The magic needs about 1 line of grammar code and about 1 line of rewrite code. This peepholing technique was explored in the early days of compiler building. In fact, the new GCC compiler uses this technique as part of its bag of tricks. I built my first peepholer using the Unix tool called AWK. It took only a page or so of code to write. I think that T to T is an even easier way of doing peepholing. Our machines are much more powerful than they used to be, so we can afford to waste some computing power to build better tools for program development. Some references to early papers are shown on this slide. I write articles about simplifying programming. Here are some places to find those articles.